Okay, so here's where we left off. This should be page 74 of your notes. We were looking at kind of conditional probabilities, and we had just defined them in that last worksheet, right? The idea of given this, we saw this a lot, probability of English given that someone was male, or the probability of English given that the student was female. So that's all we mean by conditional probabilities, sort of in this certain condition, under this assumption that the person is male, what is the probability of English? So first thing here we have is that idea of independent versus dependent, which again, we saw in that last worksheet. So this is the question we kind of tackled in class. The probability of pizza, we said in class, was around 95%. Pretty much everybody loves pizza. That probability of pizza should be the same even if we know the person is male or if we know the person is female, right? That should not change this probability of pizza because both genders like pizza a lot because pizza is delicious. So when these things are all the same, this is when we can say these events are independent. Knowing the outcome of the gender of a person does not change our probability of them liking pizza. Now, on the other hand, own a pink shirt, well, this is something that will change. So I'm actually going to use real data here because we have this because in your guys' survey, you answered whether or not you had a pink shirt. Eek, I need to find my recording thing so that I can pause you while I grab that. Here's the data with the names removed. If I go into, let's make a table. Sorry, my brain is moving slowly. A table for contingency with data, right? Contingency tables allow us to look at two variables at once, which is what we're doing. And let's look at gender versus, did I name it pink shirt? I'm sad right now because I don't know. Was there a pink shirt there and I just didn't see? I could be wrong. I'm going with this right now because it makes sense. Okay, so let's just see. This is a row percent. Shoot. Q13 is bad. Hold on, this was terrible. Oh no. Let me go figure out where my pink shirt went. Hopefully I recorded. Tragedy has struck and it looks like for some reason my pink shirt question didn't work. Dang it. So I'm going to go ahead and find an older data set last semester's to use instead. I'm super sad about it, but that's all I can do at this point. So let's find data. I want not spring because that's where I failed. I need fall. Cool. So no names. Again, I'm going to make a table. Contingency with data. And I'm going to look at gender versus whether or not people own a pink shirt, which is finally there. And I'll do row percent. Compute. All right, so you can see here, for everyone overall, the total who own a pink shirt is about 65%. So I'm going to go ahead and put that down in my lecture notes. I'm just going to probability of pink shirt for all of my students was 65%. Now the probability of pink given male, oops, I forgot my line, and the probability of pink given female, in order for this to be independent, would need to be the same. However, if you look at our actual data here, women, it looks like, was an 82%, where men were only a 49%. So a huge difference. I already forgot, 49 versus 82. So the fact that we see these huge differences tells us that this is dependent, that someone's gender does influence whether or not they own a pink shirt. So that's the idea of independent versus dependent. Again, you have this sort of rule here at the bottom. You might want to put on your note card. It's the same idea we had with pizza. That's just one way to think about our independent events.